Thank you for listening to my trial lecture. In this lecture, I will give a brief picture of where and how deep learning is used as a tool for image and video compression. First, I will introduce some basic concepts of what is image and video compression. Although image and video compression have some similarity, they are still different domains, so I will introduce them separately. Then I will talk about some special chances deep learning brings into this field, and end with a brief conclusion. So why we need compression? Let's do a simple calculation. For a 2-hour standard definition television movie, let's say 30 frames per second, size is 720 and 480 pixels per frame. And it's a color image with 3 channels. So the size of 1 second is 31 megabyte. And for 2 hours, that would be 224 gigabyte. This only for a standard definition movie. So nowadays, we would like to watch high definition movie. The size then become 1.3 terabyte. So since my laptop even cannot save one movie, how to solve this problem? We need compression. So what is compression? It's a method to reduce the amount of data to represent images and video. For image and videos, we first need to compress them to reduce the size, then transmit or store the compressed signal. On the user side, the signal can be decoded to the original or almost original image and videos. We are using these compression techniques all the time. Like when we take a photo, when we surfing online by smart mobile, or when we have a meeting. Basically, anytime we use images, videos, we are using some kind of compression techniques. So as it is very important how people do compression, why we can compress a signal and get it back later. The simple answer is those signals contain redundancy. Normally, for image and video compression, 4 types of redundancy is considered. As shown in figure A, in this figure, not every pixel is equal. Some pixels appear small, some pixels appears less. Like the star contain a lot of pixels and the white line contain few pixels. It's not smart to treat all the pixels equal. And besides, in this image, there's only 4 colors or 5 colors. So it's a waste to use 8 bits to represent only 4 or 5 colors. This is called coding redundancy. And it can be dealt with entropy coding. In figure B, if we look at a horizontal line, let's say the pixel value of this line is the same. Let's say the value is 100. So we can save it as 100 and 100 for n times. Or a better way, we can say that the value is 100 and it appears n times, which is an efficient way. And this kind of redundancy is called spatial redundancy. And another type is temporal redundancy. It's, for example, in picture C, frame 0 and frame 1, they are quite similar. They contain a lot of overlap information, except on the border side on the right, there's some shift. If we save these 2 frames, all the information, that would be a waste. And another redundancy is shown in D. For example, I have a pixel with a value of 100 and another pixel, the value is 99. For me, even maybe I don't care there's one difference between these 2 pixel values, or even I don't care the exact value of these 2 pixels. This is called irrelevant information. That's another type of redundancy. These are the reasons we can do compression, and many works have been done to reduce those redundancy for compression. Image video coding research can be back to 1960. For example, the picture coding symposium starts from 1969. Lots of research and industry work have been done since then. A series of standards are being proposed. The development of different standards also related with the progress of video techniques. Like we need a better standard for larger size of images and videos, such as AVC may not enough for 4K, so HEVC is proposed for 4K. The state-of-the-art coding standard we use now is HEVC, and the JPEG and JPEG 2000 are still widely used now. Although the use standards are developed for classical image from classical image processing and signal image processing techniques. Actually, linear-based coding is under research for a long time. The early work starts from 1980s. This early work relies on shallow neural networks like multi-layer perception. And at that time, there's difficulties to train big networks. Since 2016, along with the development of deep learning, convolutional neural networks and recurrent neural networks are introduced into image and video compression field. Some work have been reached or outperformed the classical standards. There's a hope or trend that standardize the deep learning-based methods. I will introduce more detail about image and video coding in the next section, respectively. Start with image compression. Image compression can be grouped to lossless and lossy, two classes. Lossless means after compress and decompress, we can get the signal back without loss. This kind of techniques are mostly used in such as medical imaging and technical drawing. In this kind of applications, image quality is very important and they are very sensitive to artifacts caused by lossy compression. So how we build a lossless system? When we get an input image, normally a transformation step is applied. This step transfers the original image to the format which can be easier coded. It's trying to decorrelate the input signal. Typically used transformations include DCT, wavelet transform, or from RGB space to a less correlated luminance and chrominance space, and also a combination of those methods. So after transformation, another important step is entropy coding. This step is to transfer the information into binary stream. Then the binary stream can be transmitted to other devices. When other devices receive the transmitted signal, decoding is used to recover the signal. Decoding is an inverse step and it is symmetric to the encoding part. Decoding and an inverse transformation is used to recover the image in this step. For this kind of system, the performance is how much we can compress. It can be computed by the ratio between the size of the input of the encoder and the size of the output, the bit stream. Or another format is pixel per bits per pixel, means how many bits one pixel will take. This is a lossless system, so according to channel entropy theory, it cannot compress much. Mainly the compression rate is between 1.5 to 3. So in order to have a higher compression rate, lossy system is more widely used. The main difference is for a lossy system, there's a quantization step. Quantization is to compressing a range of value to a single scalar value. As shown in the curve here, the value between this interval will be projected to 1. So quantization is a lossy step and can improve the compression ratio compared to a lossless system. So how to evaluate a lossy system? The same as lossless system, compression ratio is used. Besides, it's a lossy system, so we will lose some information of the input images. So another metric is needed to evaluate the distortion between the input image and the output decoded image. This distortion can be like mean square error, PSNR, SSIM, and multi-scale SSIM, and other image quality metric. So a lossy system wants a higher compression ratio and also want to keep as much the original information as possible. This is also called rate distortion trade-offs. So how deep learning is used in image compression? It can be divided into two groups. Use deep learning as a tool for the blocks of a compression system to improve part of the image compression workflow. Or it can be a tool to replace all the traditional blocks to the deep networks, resulting in an end-to-end framework. They are still, both of these methods, they are still under the framework of the traditional methods. Besides of this, some work are proposed for new image coding framework. They does not rely on the traditional transformation, quantization, entropy coding flow. They're trying to find out new deep learning framework. I will introduce this method step by step. So deep learning uses multi-layers to progressively extract higher level features from the input. The parameters of the network can be trained on massive dataset. It is trained by gradient descent with backpropagation method. So this requires our network to be differentiable. For layerable compression system, the first problem comes from the quantization step. It is not differentiable. Its derivative is almost zero, except the integers. So in order to solve this problem, some work is proposed, such as introduce additive uniform noise, as the green curve showing here, so the quantization becomes differentiable. And the other methods include vector quantization solutions, and the blue and also the purple curve shown here with different parameters of this method. After this, the network can be trained because it's become differentiable. So there's some work trying to learn the transformation for the better latent representation of the input signal. For the classical image compression system, for example, DCT and inverse DCT are used for encoding and decoding. Now, neural networks are proposed to replace these transformations. This gives a chance to have nonlinear transform. There are some different architecture proposed to learn the transform, like based on convolutional neural networks or based on recurrent frameworks. By this kind of approaches, the performance reaches comparable to JPEG or JPEG 2000, but still not comparable to the state-of-the-art HEVC. In order to further improve the performance, deep learning-based entropy coding also introduced. Some work directly output binary code, as shown here. The binary code can be transmitted at bitstream without entropy coding step. And also some work are trying to estimate the probability of the input data, and the probability is a key for entropy coding. And after estimate the probability, arithmetic coding is used after it. And what's noticing work is this hyperprior entropy model. The typical autoencoder network is used to do compression. Besides this, in this hyperprior network, they introduce another network to extract some side information from the latent space. The side information can improve the entropy estimation of the latent model. With this hyperprior method, significant performance boost is obtained. The model without hyperprior, and showing the purple one here, the performance is comparable to JPEG 2000, which is the green one here. And with the hyperprior model, it's shown here, this line. The performance is comparable to HEVC in terms of PSNR, and also is comparable to in terms of multi-scale SSIM. This model is optimized for mean square error, so the performance is almost as good as HEVC intro. So then the author also optimized this method for multi-scale SSRM because for deep learning models, it is quite flexible to optimize for another objective function. All we need is this, it is differentiable. So when they directly optimized for multi-scale SSRM, the hyperprior model achieves the best performance, better than HEVC, which is some line here. So another interesting work is deep learning is used to compact the input image first. Then the compact representation is sent to traditional image coding standards. This method can comparable with the traditional coding methods. And from the reported result, after applying these pre and post steps, it improves the result of JPEG and JPEG 2000. And a slightly better result is achieved compared to the original BPG. Our BPG is also comes from HEVC. It is a state-of-the-art image compression standards. But of course, it's introduced additional computational speed. Deep learning can be a tool to improve part of the image, part of the image compression workflow, like transformation only or entropy coding only. It can be a tool to replace all the traditional blocks to full deep networks, which results in an end-to-end system. They are all directly related with the traditional framework. Besides of this, some work are proposed for new image coding framework. An interesting work is proposed in 2016 by researchers from Google. The input image is encoded by CNN, and after a quantizer, the signal is sent for storage and transformation directly. Now entropy coding is used here. This is a very interesting trial, but the method is computational intensive, and the result is not comparable with H265. So after several years development, how is the result now? Here is the result analysis from a paper published on arXiv this year. I marked the JPEG and BPG with red. For PSNR metric, the performance of deep models is comparable or slightly better compared to BPG, which is this line here. And a better performance is achieved for multi-scale SSRM. And also because this network, they are trained for both PSNR and multi-scale SSRM. Still, although the method achieve nice results now, learning-based methods runtime is still cannot be real-time. So it seems there's many progress in deep learning-based image compression. How about video compression? The main difference of image compression and video compression is for video, there's a temporary redundancy. We already showed this image before. Like for example, frame 0 and frame 1, there are a lot of redundancy information. So when we're trying to code these two frames, we don't need to code both of them as majority of the information is the same. A smart way to do is to code the information of frame 0 and also the frame difference of 0 and 1. So when we want to recover frame 1, we only need to add frame 0 and the difference between them. By this way, we can get a compression ratio around 1.9. So is there any better way? Another popular solution is to compute the motion vector between frame 0 and frame 1. Then use the motion vector to do motion composition on frame 1. Then the difference between frame 1 and the motion compensated frame 0 will become small. Then we only need to save this frame difference after motion composition and the motion vector and also frame 0 to recover frame 1. This can further improve the compression rate to 2.6. This motion estimation and the motion compensation method is widely used in video coding. A brief video compression framework is shown here. A motion estimation block is added to estimate the motion between frame xt and frame x t minus 1. And this motion vector is sent to a motion compensation block to compensate this frame. And the output of this block will be quite similar to xt. And the difference between this signal and the xt is sent for compression and sent for transmission and storage. And this step is the same as image compression, including transformation, quantization, and entropy coding. Besides to send this difference, we also need to send the motion vector to the decoder side. So compared to the traditional image compression framework, the main two step is motion estimation and motion compensation. Following the same group standards, deep learning-based deep video compression can be grouped to piecemeal approaches and also end-to-end approaches. I already introduced majority of the method about each blocks, except the new motion estimation and the motion compensation. Motion estimation actually is a wider research topic in computer vision. It is called optical flow, and it can apply to video coding. So I will not go further here. I will introduce some representative work about these end-to-end approaches. One group of end-to-end work is to make a deepened version of the traditional video coding. And showing in the block on the right, every block of the traditional method is replaced with some kind of neural network. And this work is trained end-to-end to jointly optimize all the components. The loss function of this kind of network includes the mean square error, the number of bits used for encoding the motion vector, and the difference. This deepened video coding method performs better than H.264, and it achieves the comparable performance to H.265. And also the author also did some ablation study. The blank line is a result of jointly training all the blocks together, and the other curves indicate some part is not jointly trained or it is removed. It shows the benefit of jointly optimize a deepened system by an end-to-end way. It achieves the best performance as shown here. It also shows that motion information is important. This is performance obtained by without motion information. There's a big gap between the performance here. So except follow the classical video compression frameworks, there are some work trying to propose alternative new deep framework. For example, a work proposed in 2018, the authors treat the video compression as a repeated image interpolation. The key frames of a video is encoded by neural network, and the remaining frames are reconstructed by interpolation. It is benefit from deep image interpolation and get a fine performance, comparable performance with H.264. So how's the state of the art now for deep video coding? Sophisticated design deep video coding framework is proposed in ICCV 2019. The method uses a deepened version of the traditional video coding, and they extend the motion part. As I mentioned previously, the motion part is very important. The model is trained end-to-end by multi-scale SSIM metric. It outperforms all existing video compression in terms of this SSIM image quality metric. The proposed method's performance is this line here. But still, the runtime is not sufficient for real-time application at the moment. Besides the traditional compression, deep learning also brings some chances for special purpose coding. Most of the compression purpose is considered about the compression rate and the distortion. Distortion is mostly mean square error, SSRM or PSNR. There is some interesting work proposed for better perceptual naturalness and also can reach an extreme image compression rate. This purpose can be reached by generative models, including using GAN or variational autoencoder. So some researchers first proposed a work to use discriminator loss function to improve the visual quality. This is an end-to-end framework. The main difference from other neural network-based compression is the discriminator loss. This loss can encourage visually pleasant reconstructions. So by using the generative ability of GAN, it gets quite interesting result for a very high compression rate. For example, the little girl here, the original image size is 24 bpp, and after compress, it's almost like 250 times compress. And this is the result get after by this GAN-based method. We can see the output is visually pleasant. And for the same quantity level, it 2.5 times smaller compared to JPEG and JPEG 2000, and 1.7 times smaller than BPG. For this kind of generative model-based method, there's one noticeable part. It is no doubt that the recovered image are perceptually pleasant, like the original image here and the recovered image is here. It looks really nice. But it may not the same thing as the original image. Like the original building is showing in this image and the reconstructed building is showing in this image. Also, the building here looks quite nice. It's not the same building. Similar idea also introduced to video compression. For the generative video compression model, it can also generate frames which is not transmitted to the decoder part, such as in this work. Even though only 2 frames is transmitted into the decoder part, a lot more other frame can be interpolated by generated by GAN. This is the result of this work. The first rule is the original frame. Second rule are results from MPEG, which include a lot of artifacts. And the third rule are the result from the proposed generative model. It shows quite nice results. For image D, the white place is the corresponding reconstruction of the transmitted frame. It is omitted in the figure here. And the other images, for example, this one is generated. It's not transmitted from the encoder to decoder. Especially in F, only this frame is transmitted from encoder to decoder and reconstructed. All the other frame is generated by this method. So although they are generated a lot of frames, it's visually have a very nice quality. But still, there's one problem. Compared to the original input frames, it's not the same images. There are also some other interesting work proposed, like deep compression methods can be designed to carry semantic information by adding semantic analysis information into the architecture and the loss function. The semantic information can be carried during transmission or storage. This can reduce the client-side computation. The client-side don't need to recompute the semantic information again. And for neural network-based compression method, the encoder and decoders are networks. The internal representation of the images are features. So the feature maps can be directly integrated with architectures for image understanding. Then the decoding part is not needed. In this way, computational complexity can be reduced. For some tasks, it even can provide better performance. Like the result shown here, the blue curve is the performance when trained from the intermediate feature representations. We can observe that for classification, the performance is not the best, but it is the fast according to the horizontal axis. For segmentation, it performs fast and achieves the best score. There are also other interesting deep learning methods, interesting applications. I will not go further now. So when we talk about deep learning, one important thing goes to my mind is dataset. Compression does not need label ground truth. The input image is a ground truth for training a network. It can be self-supervised. So it is quite flexible to find training dataset. Like the ImageNet, which is used for classification, can be used for compression. And there are also some testing dataset for compression purpose, such as codec and the technique dataset for image compression, and the UVG HEVC test sequence for video. Besides, an interesting challenge is also organized for compression in CVPR workshop since 2018. It's designed for image compression at the very beginning. And since this year, they open a track for video compression. So in summary, deep learning can be used as a tool for individual blocks of the traditional image and video compression framework. And also it can deepen the whole classical framework or trying to propose new deep-based framework. Besides, deep learning is a flexible tool. It brings new opportunities for some special purpose coding, like use generative model to predict perceptual pleasant results with a very low, very high image compression rate. As we discussed, some blocks can be ported over to classical compression, such as learn nonlinear transforms, learn better entropy models, especially the hyperparameter-based entropy model improve their performance impressively. And for video compression, land motion estimation and motion composition is a very important step to improve their performance. And also deepen the traditional coding framework also reaches some interesting results. I only show a simple video coding framework. For video compression, there are actually more blocks can be explored by deep learning. And shown in the figure here, the blue blocks can all be explored by deep learning, like replace one or some of the individual blocks by a network, or deepen the whole workflow. There's still large space to explore in deep learning-based image and video compression, especially video compression. There are some advantages deep learning bring to this field. Deep methods, especially the end-to-end ones, can be jointly optimized, and it can adjust the objective flexibly, such as optimize for mean square error, SSIM, or other perceptual metrics. There are already some interesting special application proposed. Deep learning compression methods bring the chances to integrate it into other deep learning-based techniques. And also the traditional framework is more and more complex. More blocks are integrated into the new standards. Deep learning also brings a chance for new frameworks. Also, the new techniques bring new types of data, like depth data, point cloud, especially, for example, in medical domain. The 4K, 8K display used in operation room, and also the 3D ultrasound, they have large amount of data. And they also have very high standard for the image quality. They require near lossless compression. This brings challenges for the classical compression techniques. Maybe deep learning is a promising tool for those new challenges. Until now, the performance of deep learning-based compression is comparable or a bit better with HEVC, but they have high computational requirement. Although it's not enough for standardization now, the progress is achieved within 3 or 4 years, starts from 2016. For example, since 2017, the performance is become comparable to JPEG 2000. And in 2018, the performance become comparable to BPG. And then till 2020, seems it start to outperform BPG now. This is quite encouraging progress. Future research directions could be deep compression for new data, especially the 3D data and medical data, as I mentioned previously. And it is necessary to be real-time for compression applications. So computational efficient compression is also essential. And energy efficient compression is also very important. For example, for longer battery usage of the user side, like mobile phone, it's quite necessary to have an energy efficient compression method. And now the image quality used are mostly PSNR, SSIM, better image quality metrics, more perceptual related or human visual system related quality metrics are also interesting future research directions. Thank you.